The last thing we're going to look at for the limits section is going to be how do you evaluate an infinite limit, which means instead of having something like the limit as x approaches 3, you're going to see the limit as x approaches and then the infinity symbol or the negative infinity symbol. Now, the algebraic process for finding a limit at infinity is that you multiply every term in the expression, and a lot of times it's going to be a fraction, so that means you have to do the numerator and the denominator. Multiply every single term by 1 over x or a power of it, which means it could be 1 over x squared or 1 over x cubed or 1 over x to the 4th power. So some power of 1 over x. And then when you reduce those, as you have a limit of x to the infinity power, whenever you have a constant, it doesn't have to be 1, it could be 2, 3, 4, 5, 6. Whenever you have a constant number divided by x, if you're taking the limit as x approaches infinity for that, it will equal 0. So then usually what will happen is you'll have multiple terms, and some of the terms will disappear, and some of the terms will not. And so it'll make the expression a lot easier to simplify from there once you multiply everything by a power of 1 over x. And this rule comes from looking at the graph of y equals 1 over x. If you want to plug that into Desmos graphing calculator, basically the graph just looks something like this. And so what's happening is as you go to positive infinity, the height of the graph gets closer and closer to a height of 0. And it also happens for negative infinity. So basically, y equals 0 is an asymptote, and as you go out to the left forever, the graph to the left side gets closer and closer to 0 as well. Now, for many of these examples, multiplying by 1 over x is not going to help you. What I actually want you to do is use the graphing technique we talked about on the previous day. So, for example, on this one, I have 9 plus 3x. I would want you to bring up Desmos graphing calculator and write y equals 9 plus 3 raised to the x power. And then you may need to zoom out a little bit to get a good idea of what's happening with this graph. But they asked us two things. They asked us what happens when the limit as x approaches infinity, which means looking as far to the right as you see on the graph, and this graph seems to just be going up forever. So then my answer would be that it goes to positive infinity on the positive side. And when they say the limit as x approaches negative infinity, that means what happens when you go to the left forever for x, because here's negative 20, negative 30, negative 40. If you keep going to the left, that would be an x value of negative infinity. And this graph seems to be hitting a certain height here. It looks like there's an asymptote guiding it, and it looks like it's exactly halfway between 8 and 10. So the answer for that one must be 9. So first they said what's happening as you go to the right forever. There is a limit, and the limit is infinity. And then as you're going to the left forever, that's the difference between positive infinity and negative infinity. That's to the right, and this is to the left. On the left-hand side, there was a specific limit. It wasn't increasing forever like it did on the right-hand side. It instead was approaching a certain number, and that number was 9. Now, you may also have been able to figure that out from knowing what the graph of 3 to the x looks like, which has an asymptote at y equals 0, but then there's a vertical shift. The graph has been moved up 9 units, which is also why we're getting an answer of 9 on this one. Now, this is a graph that looks like it would be affected by multiplying everything by 1 over x, but I have to caution you that that technique was only for evaluating infinite limits. This is not a limit as x approaches infinity, so you don't want to use that approach on this one. It would only tell you what's happening on the far right and far left-hand side of the graph. They want to know what's happening at 9 from the left-hand side. So again, I'm going to use Desmos graphing calculator for this, and I'm going to type in the function 3 over x minus 9. And then you may have to zoom around to see what's happening with the graph again. Now, they specifically said what is happening when x equals 9, which would be right here on your grid. They didn't say what's happening from the right-hand side. If they had had the plus sign after the limit, then that would be going up to positive infinity. They had a minus sign after the 9, which means they want to know what's happening on the left-hand side of 9. So as I'm getting really close to 9 from the left-hand side, this graph appears to be going down forever. So my answer for this, the limit from the left, is that it's going down to negative infinity. That's the way we write decreasing forever. Once you get to number 15 on the assignment, this is when you'll see the last type of infinite limit question. This time, instead of getting answers that are positive or negative infinity, this is where you're going to start evaluating limits that are hitting positive or negative infinity. So on this particular question, we can go through the process of multiplying everything in the top and the bottom by 1 over x. So if you multiply the numerator and the denominator by 1 over x, the numerator will become 2 because the x's cancel out, and the denominator, 4x times 1 over x is 4, but I've got to distribute this, so negative 4 times 1 over x is negative 4 over x. Now we're still evaluating the limit as x approaches infinity for this. And then the rule I gave you in the PowerPoint, we'll look back at it. It says that whenever you have a constant over x for the limit as x approaches infinity, that specific term will equal 0. So going back to the assignment, that means this piece right here is going to equal 0, so it won't affect anything else in our problem, which means we just have 2 over 4 minus 0, which is 2 over 4. And you can reduce this fraction to get 1/2. So the important rule is that whenever you have a power of x in the denominator and a constant on top, those go to 0, and then you can add or subtract whatever else you need to on there normally. So our answer is that the limit as x approaches infinity equals 1 divided by 2. I'm going to show you guys one more trickier versions of this. Nothing new comes up. It's just a little bit more work of the process of multiplying everything by 1 over x. So if you look at the numerator, if we are multiplying everything by 1 over, in this case, I'm actually going to use the biggest power of x that I can. So in this case, I'm going to multiply everything by 1 over x to the 4th power. So I have to do that on the numerator and the denominator. On the numerator, that's going to cancel out x to the 3rd on top and leave me with 6 over x. And then 8x over x to the 4th would be 8 over x cubed. And negative 4 over x to the 4th, since nothing cancels from that one. And then the denominator, 4x to the 4th over x to the 4th is 4. And negative 2x to the 3rd over x to the 4th is negative 2 over x. So just look for however many x's cancel out and what's left. And then on the last one, nothing cancels, so it's negative 7 over x to the 4th. And then when you're evaluating the infinite limits, for this one, I have a constant. Oops, that's supposed to be over infinity. I have a constant over infinity, so that equals 0. And then I have another constant over infinity, so that equals 0. And then another constant over infinity, so that equals 0. Now on the bottom, we have 4 minus 0 minus 0, which means our final answer here is actually 0. And just to explain what's happening, the reason the limit as x approaches infinity for a constant over x, the idea is that you're taking a set number like 6, and if you divide by something like infinity, or imagine it's just an insanely large number like 1 trillion, kabillion, bazillion, that number is so close to 0 that we essentially treat it as 0 anyways. So that's what's happening when we're evaluating the limit as x approaches infinity. We're saying, let's think of x values that are absurdly large. Well, a small number like 6 divided by a number in the trillions is so close to 0 that it's essentially the same thing. That's why we're able to do this process here, and it's why we're able to simplify a lot of the limits. So that's all for the notes, guys. Thank you.